Good day, students. Welcome to the AP Calc AB Mock Free Response Questions Review. We're going to be taking a look at the graph of the derivative of a function in this installment. We're going to be solving problems that involve the use of the fundamental theorem of calculus, finding the extrema, concavity, and points of inflection of a function, find the mean value theorem, finding the critical points, and also generating the equation of tangent lines. All right. So let's go ahead and take a look at the problem. So it says, let g be the continuous function defined on the interval -6 to 5, whose graph consisting of two quarter circles. As you can see here, there's a quarter of a circle, a quarter of a circle, a semicircle. This entire graph right here is a semicircle, and a line segment. So there goes your line segment. Let g be the function given by g of x equals the integral from -3 to x of f of t dt. So let's take a look at part one. We are to find two things. We're to find g of 3 and g of -6. So let's start off by finding g of 3. So number one, I want to find g of 3. So what are we going to use? We're going to use this formula right here to compute what the value of g of 3 is. There's one more detail. This graph right here is a graph of f. Okay? All right, so let's find g of 3. G of 3 is going to be the integral from -3 all the way to 3 of f of t dt. So all I just did is with this x right here, I just replaced it with 3. Okay? So to find the integral of a function, the definite integral, if you have the graph, the graphical approach will involve finding the area. Okay? So we're going to use a geometric approach to evaluate this definite integral. So anytime you see a graph problem that involves geometric figures, lines, or semicircles, in most cases, you have to use your geometric formulas to determine what the area is, which is the value of the definite integral. Okay, so what is the area from -3 to 3? From -3 to 3, you just simply have a semicircle. Okay, so what is the area of a circle? We know that the area of a circle is pi r squared. In this case, we're going to be looking for the area of a semicircle, but it's going to be inverted, the bottom half, okay? So the area of a semicircle, the bottom piece of a semicircle that's residing beneath the x-axis is going to be negative pi r squared, area of the circle divided by 2. The reason for this negative is because it's below the x-axis, all right? So we have to keep that in mind. Okay, so this definite integral is going to be equal to negative pi r squared with 2. What is the radius? The radius of the circle, as you can see, is 3. So it's going to be pi times 3 squared over 2. And if you work that out, you're going to have negative 9 pi over 2. Okay? So that's the value of g3. Now let's look for the next one, g of -6. So g of -6, let's see. We're going to basically be evaluating this expression here, the integral from -3 to -6 of f of t dt. Okay? One thing you want to note is that the integral, the limits of integration are in decreasing order. Okay? So if we want to evaluate this in the increasing order, we have to reverse the limits of integration. So that's going to give us negative the integral from -6 to -3. Okay, so if you're going from left to right in increasing order, that's basically what we're looking for. So we have to reverse the limits of integration and introduce this negative sign right here. Okay, so f of t dt. All right, is nicely ordered for us. Now we are going to find the area underneath the curve for this region between these boundaries, okay? So from -6 to -3, what you notice is that we have two things happening here. We have a quarter of a circle, and we have a line segment. So what must we do here? We must divide it into two separate integrals, okay? So we're going to break it up into negative the integral from -6 to -5 for the quarter of a circle, plus the other one. But if I distribute this minus to the plus right here, it's going to make it a minus, okay? Minus the integral from -5 to -3 of f of t dt. That will take care of the line segments. Okay, so we're looking for these two areas right here, this area underneath, and then this other area here. So this entire region, that's what we're looking for the area of. Okay, all right, now let's go ahead and take a look at the formulas that we're going to use to determine the area for these two regions under consideration. So this is a quarter of a circle, but we have a unique situation here. We have to look for this area. So how do we look for that area? In order to find that area, we're going to be subtracting the area of the quarter of a circle, which is going to be this area right here, and then we're going to be subtracting it from the area of the entire square. Okay, so let's take a look at what that looks like. We have a square like this. Okay, try and draw it as best as I can, and then we have the quarter of a circle right here. Pardon my for looking a quarter of a circle. Let me try it again. So you have a quarter of a circle. So we're looking for this area right here. So let's see, this is a quarter of a circle, so this is R and R. So the area of the square is basically area of the square is R square. Okay, and then area of that quarter of a circle is the area of a circle divided by 4. So it's pi r square over 4. So this remaining area right here that we need to find is going to basically be the area of the square minus the area of that quarter circle right there. Okay, so we're going to have area of a square is r square, and an area of a quarter of a circle is pi r square over 4. So that's basically the value of this definite integral, the first definite integral that we're looking for, the area from -6 to 5. Okay, so let's go ahead and put that in here. So we are going to have negative, don't forget that negative piece, r square, the radius of our quarter circle is 1. How do I know that? Well, let's go back here. You can see that this is the radius right here. From here to here, that's the radius of our circle, which is 1. Okay, quarter circle. So r is 1. So we're going to have r square, which is 1 square, minus pi times 1 square over 4. So that's the area of the area of the region underneath the quarter of a circle. Okay, now let's find the area underneath the line segment. So this line segment right here, we have this area. We already computed this area. The area underneath the line segment is basically the area of a triangle. Okay, so let's go ahead and write down the formulas for that second region we're computing the area of, which is a triangle. So when you are finding the area of a triangle, the only two things you need are the length of the base and the height. Okay, and if you have those two measures, you should be good to go. Okay, so what is the area of a triangle? Going back to elementary geometry, the area of a triangle is 1/2 base times height. So we just need to find the base and the height of that region between -5 and -3. So the base, as you can clearly see, is 2 and the height is 1. All right, so the base is 2, and the height is 1. So now we're ready to evaluate this second definite integral right here. So we already distributed the minus, so we are not going to be adding the integral. So it's going to be minus 1/2 base times height, 1/2 base of 2 times the height of 1. All right? If you simplify this piece, we'll have negative 1 plus pi over 4 minus, these two 2's cancel out, 1 times 1 is 1, 1. If you combine these two, you have negative 2 plus pi over 4, or pi over 4 minus 2. Okay, so the second part of question 1, g of negative 6 is equal to pi over 4 minus 2. So there you go. So we just found this area, the area underneath the curve from negative 6 all the way to 3, to negative 3. It's a composite area. All right, now let's move on